Bienvenidos, Ushamdi, and welcome CTS230 Section 841 students for the first 8-week term of the fall 2017 semester at Anne Arundel Community College. This is the Networking 3 or the Scaling Networks version 6 course, and this video tutorial is going to be a supplement to the material that we've covered in Chapter 3. I'm going to break this down into a series, break down the supplements into smaller, more digestible bites here. And so in this supplement, we're going to be focusing solely on Layer 2 traffic engineering. Specifically, we're going to be looking at that port cost command, and we're going to be looking at the port priority command, where with spanning tree, we can change the cost on an interface and we can change the priority. But there are some considerations that we need to make sure that we're aware of, and we need to understand how those commands are going to affect the root bridge and a non-root bridge when they're applied. And this is the question that we had last night when we were taking a look at the multiple links. And so again, this is going to be a very inductive approach here, and we're going to walk ourselves, and I've got two real Cisco 3750 switches connected together here. And so here's what we're working with right now. And so let me pull up the drawing tool very briefly here. All right, so as I said, we simply have two 3750 switches, and we're going to call them DLSW01 and DLSW02. And so this will simply be switch 01, and this over here is going to be switch 02. Now, these switches have 8 Ethernet connections that run between them. And so let's draw those in here. 5, 6, and I think we're going to have to go high here. 7, and we'll bring the last one down here, 8. So all 8 of these connections are plugged into these two switches, and I'll just say switch here. So let's walk through this. So the first thing that we want to do is we want to determine which of these two switches is going to be the root bridge. Now, there's only a single VLAN in play here. It's VLAN 1. But this conversation, given that we're making the same switch the root bridge for all VLANs, this conversation would be the same if I had 1,000 VLANs on here, or if I had 2,000 VLANs on here. So how do we determine the root bridge? Exactly, it's all based off the bridge ID, right? And we talked about that BID value because we need to establish which of these two switches is going to be the root bridge. That way spanning tree, and again, these are all going to be trunk ports. We're going to do that configuration, but we need to figure out who's going to be the root bridge so that spanning tree can determine which ports are going to be forwarding and which ports are going to be blocking here. And remember that the bridge ID consists of the MAC address. It consists of the bridge priority, I'll just say BPRI, and then the system ID extension. So I'll just say SIE. And remember, that's nothing more than the VLAN number. And remember that we've talked about this ad nauseum, that value is simply added to the bridge priority. But if we've got two switches and they all have the same VLANs, and we're talking about the same VLANs, that system ID extension value is never going to swing the root bridge election, right? It's going to be the bridge priority, and if the bridge priority is a push, in other words, if the bridge priority between these two switches is equal, then it's going to come down to the MAC address. And again, it's very simple. Remember, with spanning tree, lower is always better. And there will never, ever, ever be a tie. Lower is always better. There will never be a tie. So let's transition back to our two switches and let's determine we're going to make these trunk ports, and let's determine of these two switches, DLSW01 and DLSW02, which switch is going to be the root bridge, and more importantly, we need to understand why. Why is a given switch going to be the root bridge? And so here we are on DLSW01. I'm going to go from user exec to privilege exec and then into global config. And now I'm going to go into the range, interface range, fast Ethernet 1033 all the way to 48. In fact, I should have said there's actually 16 connections running between these that we'll be taking a look at here. And again, this is to drive home a very important point, one that we spoke about last night. So I go into this interface range command, I say switch port mode trunk. Now, why can't I do that? I'm on a 3750 switch and I get this auto error. Now, I'm going to do a supplement specifically on this error. So we'll come back to this, but we know we need to say switch port trunk encap.1q. We need to hard code the encapsulation before we say I'm going to hard code you as a trunk. Now, let me come over to DLSW02. You can see the same interfaces are reacting here on DLSW02. So let's go from user exec to privilege exec into global config, interface range fast Ethernet 1033 to 48. And we're going to do the same thing, switch port trunk encap.1q, switch port mode trunk. Now, I could also say switch port no negotiate, not focusing on that right now, but we'll go ahead and throw that in there. Now, on switch 2, and actually I'll come back to switch 1. So we'll start over here on switch 1, and I'll put the switch port no negotiate in here, and I'll say end. So when I say show not show VLAN brief, show spanning tree. So here I am looking at the 16 ports that are running between switch 1 and switch 2. Now, what do you notice about the role and the state of the bottom 15 ports? Yeah, again, it jumps right out at you, right, that these are all alternate ports and these are all blocking ports. In fact, there is a single fast Ethernet 100 megabit per second link that has been selected as the root port. So we're not even on the root bridge, which at this point we can conclusively say is DLSW02. And the reason that we can conclusively say that is because the root bridge for the VLANs for which it is the root bridge will never have a root port. So let me say that again. The root bridge for the VLANs for which it is the root bridge. In other words, if we had that topology that we've seen in the packet tracer activities like this, where we split and we say VLAN 10 and 20, switch 3 over here, that'll be the root bridge. And for VLANs 30 and 40, switch 2 will be the root bridge. And so that's what I'm saying here, is you could see a root port on switch 3, but it would be for VLANs 30 and 40, for which it is not the root bridge. And again, here we're working with a single VLAN to try to keep the explanation simple. So again, I can conclusively say that this is not the root bridge. In fact, if I clear the screen here, we had some output just a little higher up that we could also take a look at and say, here is the root bridge information. And remember, with legacy 802.1d 1998, the Cisco implementation of that is PVST, PVST plus. We're doing 802.1q, so we are PVST plus. The root bridge is the only switch in the layer 2 domain that is sending, or I should say originating, BPDUs. The BPDUs that are being forwarded along by other switches are simply mere images of the BPDU that originates from the root bridge and then is sent down to all of the non-root bridges. But this is the root bridge ID and information, and here is the MAC address for the root bridge. Here is the MAC address for this local bridge ID, in other words, the switch that we are on. Now, it's interesting, these are real 3750s. The first 4 hexadecimal characters are the same. In fact, the first 6 hexadecimal characters are the same. It's not until we get to the 7th hexadecimal character that spanning tree and the switches that are participating, which is simply DLSW01 and 02, they both initially say, hey, I'm the root bridge. Then they exchange BPDUs every 2 seconds. And what ends up happening? They both determine that, well, no, we're not both the root bridge. It's DLSW02 because it has a lower MAC address, because it's got the 6 here and this guy has a 7. So the first thing that we needed to determine was who was going to be the root bridge. The bridge priority is the default of 32768, as you can see here, right? And again, we're adding in that system ID extension, which ultimately is never going to swing the root bridge election, because we're saying that we're dealing with the same VLANs. That's the scenario, the use case we're talking about. So, given that I've got 16 connections between these 2 switches, and I will not draw all 16 in here, really what we have when we look at this is we have a single connection on fast Ethernet FA1033. And that has been elected as the root port, and that is the only port of the 16 ports that run between switch 1 and switch 2 that is actually forwarding traffic. Everybody else is blocking. So, and I've walked into shops before that have, and it hasn't been 16 links, but it's been multiple links that are all trunk links. And remember from our conversation last night, by default, a trunk link is allowed, or let me rephrase that. By default, which VLANs are allowed to transit a trunk link? And the answer is all. Every VLAN that exists by default is allowed to transit the trunk link, right? So if I've got all these servers over here, and I'm thinking that, hey, I've just put in multiple links between these switches because it's a great idea, I want to have redundancy. You definitely have redundancy, but what you don't have is you don't have an aggregate of the available bandwidth, right? And so that's where I'm going to stop that conversation, right? Because that's the segue into the ether channel conversation. So let's say initially you're a small shop, you've got these PCs out here that are all hooked up, and maybe they're all on the same VLAN. But here's the problem, is spanning tree is going to select a single and only a single root port on the non-root bridge. And only that single root port is going to be allowed to forward traffic. So we talked about the point of diminishing return in a design like this, where, okay, do I want to just have one link? Well, obviously not, because what if that link were to fail? So I'm going to put a second link in here, because that, that makes sense, right? To have a second link for redundancy. What starts to maybe not make sense, and again, I'm dealing with 3750s fixed. Well, actually, you can stack the 3750s, but let's say for the sake of argument that they're 48 ports each, and I'm not going to be able to stack them. I'm fixed at 48 ports, and it's just these 2 switches. Does it make sense for me to run a whole bunch of cables between these and leave them as trunk ports? And you can see right over here that no. So one, obviously we have to have one in order to have this communication, because maybe this switch goes to our router that connects to the Verizon Fios internet that we have that gives us connectivity out to the internet, right? Maybe that's how this is set up. But again, the fundamental idea of redundancy is met with two connections. Now, if it's a 48-port switch and maybe you don't have 40 hosts over here, okay, sure, you can put a couple extra links in, but again, if you're not going to do the ether channel of these links, you should think about, how many ports does it make sense to put here, understanding that with this scenario, with switch 2 as the root bridge, all of its ports will be in the forwarding state, and we're going to see switch 2 in a second, and they're all going to be designated ports, because remember, by default, the root bridge, right, will have designated ports for all VLANs for which it is the root. So they will all be designated ports, they'll all be forwarding. The problem is over here. And this was the catalyst behind Ether Channel, was that if I've got spanning tree, that's great. It's preventing loops here. That's exactly what we want. The problem is that when I'm running these multiple connections, I'm only using a single connection. It may look like I've got various things going on. And right now on my 3750s, just like we saw last night on the 2960s in class, the little green arrow, and actually that was a terrible draw there, and actually here I'll switch to green in fact. So remember the little green arrow above each of the sets of ports that look like that, right? So right now on this switch over here, on switch 2, all of the arrows are green for all 16 ports, right? The arrows are all green. Over here, only the root port FA1033 has a green arrow on it. All of the rest of the ports are orange because they're blocking, right? They're alternate ports that are blocking. They are not, and let me pull this back up, you can see right here, you can see they are not forwarding. And so that's what we have. So now let's go ahead. Now that we understand how to select the root bridge, and now that we understand why we're seeing this output here with these 16 links that run between these two switches, and only one on the non-root bridge has been elected as the root port and is in the forwarding state. If we take a look over here at switch 2, we'll go from user exec to privilege exec, and I'm going to say show spanning tree. And as promised, this is exactly what we see. All of the ports on the root bridge for all of the VLANs for which this is the root bridge will be designated for the role, and the state will be forwarding because it is the root bridge. And again, we're dealing with a single VLAN to try to keep things, because I don't want the output from 100 VLANs here, because the conversation is the same, given that this switch is the root bridge for all VLANs in my environment. So we can clearly see here that this is the root bridge, and if I went up just a little bit more, you can see that the root ID is that MAC address, and it's no coincidence that the local bridge ID is the same as the root bridge ID. Again, proving that this is the root bridge. Now, what's the cost going out the interface, right? We're at fast Ethernet for all of these interfaces. So now let's talk about those two commands that we're interested in, right? Changing the spanning tree cost of a port and then changing the priority. Because here's the question. Given that we've got these 16 links running back and forth between these two switches, we know why this switch is elected the root bridge. And we know that these are all designated ports because it is the root bridge. And we know that only that port has been elected as the root port. And so the question becomes why? Because there will be cases, and I can almost guarantee that you would never see on a Cisco exam something simple like this, that's then going to ask you, which port is the root port. They're going to have a second link in there somewhere, or they're going to have a switch dangling off over here and ask you between these two switches, which port would be which port would be blocking and on which switch, or which port would be elected as the root port, which port would be the designated port, right? And they're going to have multiple connections, which are both pure trunk ports between the switches. Now remember, we're talking about trunk ports here, because by default, these are both dynamic auto. So by default, they negotiate to an access port, but that's not what we're dealing with. We've set these, hard-coded these, trunk in cap.1q, switch port mode trunk. So now we go back to this conversation. Why is this the root port? What about the other 15 ports that I have there? How come those didn't get selected? And so here's kind of the algorithm that we're going to follow, if you will. So the first priority that we have here, right? All right, let me say task. I don't want to confuse you between the priority of the port priority. So the first task that we have is ID the root bridge. Well, we've done that, right? We've ID'd the root bridge. The next thing we need to do is determine on the non-root bridge which port or ports will be the root port, and which port or ports based off of that are going to be forwarding and which are going to be blocking, right? Our alternate blocking ports. And so for whatever reason, Fast Ethernet 1033 has been elected as the root port, right? Switch 1 has said this is going to be the root port. Now, here's the question. Why? Why is that the root port? Well, the first thing that we need to determine, once we've defined the root bridge, we have to determine the root port. Well, the root port on the non-root bridge is based off of, number one, the lowest root path cost, right? The lowest root path cost. Well, what is the root path cost for all of these ports? Because they're all Fast Ethernet interfaces, so it's 19. So it's a tie for all 15 interfaces on switch 1. So if lowest root path cost is a tie, then how do we break that tie, right? Because again, we're saying that we've got redundant connections here. And we're saying that the root path cost is going to be the same, because we know that the sender's bridge ID is also going to be the same, right? So that was a tie, and actually maybe technically correct here. Let me go ahead and drop a little 1A in here. So don't forget that we've got the sender's bridge ID. But again, the bridge ID is only the MAC, the priority, and the system ID extension. So that's going to show up and be the same over here as well across all of these ports. So we see that there's a tie in the bridge ID, right? The sender bridge ID. We see that we've got a tie there. Then we see that we've got the root path cost is also a tie, right? So the root path cost is 19 for everybody. So then what's the tiebreaker? And this is where we need to exercise caution, because here's the statement that gets made. Oh, and it's all about perspective. And these two commands that we're talking about, it's all about the perspective, right? We have to ask from the perspective of which switch. So you hear the statement get made. Oh, well, it's just then, if it's a tie between the root path cost, it's simply the lowest port number, right? It's the lowest port number. Now, that is not technically correct. This gets said a ton, but it's only true if and only if every single interconnection between these switches is using the exact same port numbers. In that case, it would be the lowest port number, but it's the lowest, and this is very important, by default, it's the lowest sender's port ID. And so let me explain what I'm saying there. So we have switch 1 here. It's not switch 1 that is making that election as the root port, right? Ultimately, it's switch 1 that puts it into forwarding, but because every link is the same cost, it's going to be the lowest sender's port, and I'll say port priority, lowest sender's port priority, right? Which corresponds to the lowest port number 99.9999% of the time, but it's the lowest sender of the BPDU. So the root bridge is sending the BPDU, because remember, it's only the root bridge that's sending BPDUs. So the root bridge is sending the BPDUs. It is dictating what that root port is going to be, okay? And that's when we get down to that quote-unquote, that lowest port number, which we're going to refer to as the lowest sender's port priority. Now, you're probably saying, well, I know we can do the spanning tree command. I'll say spanning tree, port priority, port dash priority, and I can set it, I think it's 0 to 200 and something, maybe 256 or 240 in increments of 16, right? So let's prove that this is correct. And here's how we're going to prove that. I'm going to go over to switch 1, and here's where the confusion with these two commands comes into play, is that learners are under the impression that if I go in, I'm going to go into interface fast Ethernet 1044, right? So let's say do show span, and let's prove that 44 is not in the forwarding state, it's in the blocking state. The roll is an alternate port, and I'm going to go ahead and say spanning tree, port priority, and let's get these, yeah, it's 240, it goes to 240, so 0 to 240. And I'll say 16, right? And this is the most common mistake that gets made, is the port priority is changed on the non-root bridge. In other words, it's changed on the bridge that is not originating the BPDUs, that's not sending the BPDUs. And let's say, do show spanning tree, and we'll come down here again, and you can clearly see, right? The cost is still 19, but why is this not the root port? And it's because it's the sender's port priority. It's the lowest sender's port priority. The root bridge is the sender, right? So what is the takeaway here? The takeaway is simply this, if you're using the spanning tree port priority command, the spanning tree port priority command should be used only on the root bridge, because it's only evaluated if there's a tie between the cost of all the ports and if it's coming from the root bridge. So I'm going to change this back. We're going to go over to the root bridge, DLSWO2. I'm going to go into global config. We're just going to pick interface fast Ethernet 1039. And we're going to say the same thing. Spanning tree, port priority 16. And in fact, let me do this. Over here, we're going to say do debug spanning tree events. And let's watch and see what happens. Because this is the root bridge. I just made the change. And let's step over here and see if anything is going on. And take a look at what has happened immediately. Spanning tree is now reconverging. And before I draw anything, I'm going to let this play out. And again, this is legacy per VLAN spanning tree. And take a look at what happened. We ran the command over on the other side. We changed the port priority on FA1039. It immediately transitioned into the listening state. And you can see right here, down to the millisecond, it put 33 in the blocking state because it fired the BPDU over. Switch 1 says, it gets that BPDU and it says, hey, spanning tree, we're going to reconverge. And now I need to reevaluate because I'm being given a sender's port priority that is lower, right? You can see here, look, new root port FA, whatever, the cost is still 19. But it's the port priority that changed. So it says right here, fast Ethernet 1039, it goes from the blocking into the listening. And then we've got that 15-second forward delay, right? And a quick side note, take a look at this. It transitions from forwarding to blocking immediately. And it has to because we have to prevent spanning tree loops. So it drops it into listening on FA1039, and then take a look at this. 004013, 004028, the delta there is very familiar. There's that forwarding delay. Transitioning from listening to learning, 15 seconds. That's that value. And I transition into the learning state. And then look here, isn't this interesting? 28 to 43, another 15 seconds. And then I transition into the forwarding state. But again, the only reason that this is happening is because the sender's bridge ID, I'm sorry, the sender's, I apologize, the sender's port priority, the sender's port ID, if you will, is lower for this port, FA1039. So setting the spanning tree port priority command is going to impact and allow you to do layer 2 traffic engineering if and only if it is set on the root bridge side. If you set this on the, oops, that's terrible in there. If you set this on the non-root bridge side for the VLAN in question, what did we see? We saw that it has no effect whatsoever. So that command, spanning tree port priority and then tweaking the port priority, we can manipulate and do traffic engineering, but if and only if we are applying this command on the root bridge side of things, right? So now that begs the question, right? Let's take this to its logical conclusion, which is, okay, well, but you said that the cost is evaluated first. And so that's why we did this first, right? And you can see that we're on the non-root bridge, but it is still reporting, again, it's getting it from the sender, right? It's getting it from the root bridge. And that's a critical point. But you're right. And when we look at this here, we can see, and I think if I hold Control down, I can get just that column maybe. No. Let me see if it's Alt. Uh-oh. Make sure we didn't cause any issues here. So if I hold Alt down, yeah, if you hold Alt down, you can just get that column. So you can see that the cost, which is evaluated before the port priority, is equal. And that's why we had to go to the port priority to make the determination. And this value here, remember, it was all 128. And that's where that statement comes from typically, where you'll hear people say, oh, right, so then switch 1 picks the lowest port. Well, again, if it comes down to the port priority, which if the cost is the same, it does, it's not really switch 1, it's the lowest sender's port. But again, that's typically the lowest port number. But be aware that it's being picked on what the sender, the root bridge, is sending, what the root bridge has set in that port priority command, right? So let's say we want to do some additional traffic engineering. For whatever reason, I had this set. I don't want to reset it. I want to change it on the non-root bridge side. And now we open our conversation on the spanning tree cost command. So if it's true that the cost of the port is evaluated before the priority, let's see if that's the case. So if I go into interface fast Ethernet 1044, and I want that to be the root port on the non-root bridge, and I want this port to be the forwarding port, I can say spanning tree cost, and now I can put in a value. And again, you can see the values go to, and what is that? Is that 200 million or 20, 1, 2, 3, 1, 2, 3, 200 million. But again, lower is better. So I'll say, okay, let's set this, if 19 is what it's set to, let me see if I set this to 10, if that is going to influence what happens here. And take a look at this. We immediately transition, new root port, because we have set one of the evaluation criteria, specifically the one that's evaluated before the port priority value, the port cost. We've set this to a lower value than all of the other ports. And if you're thinking, yeah, this is going to take 15 seconds to go from listening to learning, and then 15 seconds to go from listening to forwarding for 44, you are absolutely correct. So what do we have here? 03, 18, 33, 15, 15. That is your forwarding delay. This is why 39, which was the root port, goes immediately into the blocking state. We listen, right? We learn MAC addresses, and then we figure out that, yep, we're going to transition into the forwarding state. And so a quick side note, when we configure port fast, this is exactly what port fast is facilitating. Port fast facilitates for access ports that are connected to PCs, servers, access points to nodes, right? That are not going to be running spanning tree. It skips listening and it skips learning and transitions immediately to forwarding. So we wipe out that 30 seconds that we were just kind of sitting here waiting for something to happen, right? Because that whole time spanning tree is converging right there. Traffic between switch 1 and switch 2 is not flowing. And so let's prove that. And how would we prove that? I would simply go into interface VLAN 1 and say IP address 10.0.0.1. And this was the statement that was being made in the text, that when spanning tree is reconverging for whatever the topology is and the VLANs that are associated with that reconvergence event, traffic is not going to flow. So here we go. And we'll say no shut. Duplicate. Oh, sorry, duplicate address. I put the wrong address here. My bad. All right, let's get back to that. There we go. All right, so now we're there. No duplicate address. So do ping 10.0.0.1. Let's confirm that connectivity is fully functional. And there it is. Let's come over to switch 1. And we'll say do ping 10.0.0.1. Ping myself. Got to get these IPs straight in my head. 0.2. So there we go. So we've got connectivity without a doubt. So here's what I'm going to do. Over here on switch 2, I'm going to kick off that same ping command, and I'm going to put a ridiculously high number of ping packets in too many. And there we go. So traffic is flowing. Everything is great. And then I decide, do show span, and let's take a look at where we're at right now. Right? The forwarding port is that port because we changed the cost. The cost has changed, right? So let's go ahead and say 37. Interface fast Ethernet 1037. I'm going to say spanning tree cost because I'm manipulating, I'm performing layer 2 traffic engineering on the non-root bridge, knowing that to do that, I need to be using and manipulating the cost value, not the port priority value, the sender's port ID value, right, which is going to be these values here. So spanning tree costs, and let's make it 9, or actually make it something a little different, 7. So let's see what happens here. Well, take a look at that. This is interesting. So we moved into listening, and it immediately blocked 44. Well, what is happening over here with those pings? Now remember, I've got 16 trunk ports between these two switches, yet no traffic is passing because only a single trunk port on the non-root bridge is ever going to be, if I said do show span, let's see if I can catch it before it gets to, I missed it, I apologize. I was trying to catch it when it was in the LRN or learning, or when listening, learning. I was trying to catch it. But again, the point is still proven that traffic, while spanning tree was reconverging, sat there. That is a 30-second outage right there, right? Not a good thing to have happen. And so again, 16 links between these two devices. We can see that spanning tree is going to have to reconverge, and we can see that no traffic was flowing. And again, 16 links that are all, I've got link lights on all the links, but spanning tree on the non-root bridge is only allowing one of these links because it has to avoid loops. It's only going to allow one of those links to be in the forwarding state, and only one of those links is going to be able to pass traffic. And again, this is very, very important what we talked about in terms of the application of layer 2 traffic engineering using the spanning tree cost command, which is only going to be effective on the non-root bridge side, and then the spanning tree port priority command, which is only going to be effective on the root bridge side. Okay? And that last one, the port priority, only comes into play given that the costs for all of the links between the two switches are identical, right? Are the same. And so let's prove Control-Shift-6 to kill that. Let's go into interface fast Ethernet 1/0/30. What do I do? We'll do 42. We'll just pick a random port. And I'm going to say spanning tree cost 1. Is that going to influence? You'll notice, see the little blue triangle that kicks up when something happens here? We're debugging spanning tree. Did I see anything go down over here? No, nothing. Why did nothing happen? Because it's the local route path cost. In other words, the perspective, my route path cost. And when I say my, I'm saying DLSW01. That is evaluated first. So from the perspective of the non-route bridge, I evaluate the route path cost. Right? That's the first thing that I evaluate in trying to determine which port's going to be my route port. When I have multiple ports with the same cost, then we transition to the lowest sender's port priority value. But that port priority value is coming from the route bridge. He's the sender of the BPDU. And therefore, he will drive the route port selection if you're using port priority on the route bridge, which is the only place that is going to have an effect. All right, so we've talked about a lot here. Now you can start to see that, okay, well, I really like the idea of ether channel a lot better than dealing with 16 trunk ports or 8 trunk ports or even 4 trunk ports. And so think about, these are the things that you need to think about, right? To sit and reflect. When do we get to the point of diminishing return in this kind of a scenario? And it's probably after the second port. Now, if you're dealing with a modular chassis of some kind, which 68, let's say a 6513 that has 11 payload slots, and you've got 2 of them, and you're running the links between them. And these are the line cards, right? So absolutely, you want to put them on different line cards. And, maybe it makes sense, right? You do 4 like that. But again, keep in mind, you're wasting these 3 ports on those 3 line cards until and when and only when that link fails. And then it will simply go to the next port. And so, again, and this is sort of going to, while we're on the topic of point of diminishing return, where you want to get crazy, is inside of the switches there are ASICs. And so the 3750s, they have a single ASIC, but the newer switches, like the 3650, has 2 ASICs in the 48 port module. So maybe you want one of the trunk links coming off of ASIC 1 and the other trunk link to go into a port or one of the ports that's using ASIC 0, right? And so that's something to think about, because theoretically it's possible that if an ASIC were to fail inside of one of the switches, that the ports that are not connected to that ASIC are going to stay up. I have never seen that happen. I've always seen when an ASIC fails, that there are always issues of some kind. But it doesn't hurt. Maybe it buys you a little extra time. But again, this is kind of like, that's kind of ridiculous to be talking about that. But it all depends on how granular you want to be when you're talking about your inner switch links. And again, once we start to talk about ether channel, this is still a valid point. Okay, yeah, let's put it on ports that are in different ASICs. That's not a bad thing. Let's figure that out, and let's do that. But with a switch that has a single ASIC, it really doesn't matter. And would you put 16 trunk links between 2 switches? Probably not. Would you put 4? Maybe. But again, you've got to think about the use case. What are you trying to achieve? What are your goals? We get redundancy with 2 links, right? So maybe that's good enough, and we save the other 46 ports for access ports in order to plug things in. But again, to quickly recap here, it's all about those 2 commands when we're doing that layer 2 traffic engineering. And so remember that. If you're using port priority, you have to use it on the route bridge to be an influencer, but it's only an influencer when the cost is the same between all of those redundant links. And if you're going to use the cost, you're going to have to use it on the non-root bridge side, because that is where it's evaluated before you get to the sender's port priority. And remember, when you hear people point to the switch and say, oh yeah, it just uses the lowest port number on that switch. Well, that's if and only if every port that's running between those switches is plugged into the exact same port on the other side. Because if I reverse the cable between 33 and 34 on the root bridge side, 34 would be elected because it's sending the bridge ID for 33. And in fact, let me pause and we'll do that and we'll see what happens. All right, so for our final proof of concept, what we were going to do was switch the cables in Fast Ethernet Fast Ethernet 1033. I just switched 33 and 35, the two ports that were on the top. But what I did was I switched them on the root port side, or I'm sorry, on the root bridge side. So if we were to take a look here and I say show span, you can see that this is the root bridge. Again, all the ports I set back to basically, I removed all of the port priority and cost commands, so everything's back to the defaults. And so you can see right here, everything looks good here on the root bridge. But remember, it's on the root bridge where I crossed the cables for Fast Ethernet 1033 and 35. So what we have right now is we have over on the non-root bridge, so in other words, over on switch 1, we'll draw this out, on switch 1, Fast Ethernet, this is kind of lagging behind here, 1033, right, actually goes to the root bridges 1035, and the root bridges 1033 goes to FA 1035. And so this is going to prove, right, conclusively show that it's the sender's port priority, right? It's going to be your sender's port priority. And so if that's the case, which port on the non-root bridge, switch 1, which port will be the root port? Because the costs are all going to be the same. I removed all the cost commands, right? So exactly, we should see Fast Ethernet 1035. So let's check and see if that's true. And that is going to wrap up, again, our layer 2 traffic engineering deep dive here. So show spanning tree, and hopefully this is going to yield the results we're looking for. And absolutely fantastic. Take a look at that. So when the cost is the same and you've got multiple links running between the two switches, it'll evaluate the cost. That's a non-root bridge influencer, and you'll see that it's the same. And so then we go to the port priority, right? Or the sender's port priority. And that's what people mean when they say, oh, the lowest switch port. But again, be careful, because it's definitely the lowest switch port, but not from the perspective of this switch, right? From the perspective of the root bridge. All right, well, hopefully this is explained in a nice and clear fashion exactly what you're going to need to know about layer 2 traffic engineering with spanning tree. You've got a great understanding now of the port priority as opposed to the cost command, and on which type of bridge you would use those, and what they're going to do when they're evaluated, and how they can help you do your layer 2 traffic engineering with spanning tree. All right, so that's all we've got. I'm going to do another one, and we're going to talk about that auto error that you get when you try to turn it into a switch port mode trunk, but it's set to dynamic auto. All right, guys, thanks so much for watching. I will see you next Tuesday.